Welcome back to G Fun Facts Online. Today we are going deep underground into the silent, subterranean world of global telecommunications to discuss a revolution that is built on absolutely nothing. For the last 50 years, the backbone of our entire digital civilization, the internet, international banking, military comms, has been built on strands of ultra-pure glass. We call it fiber optics. It has been a miracle of engineering, guiding pulses of light across oceans and continents to connect us all. But standard fiber optics has a flaw. It has a fundamental physical limit that no amount of software or engineering can bypass. The issue is that inside solid glass, light slows down. For decades, physicists and engineers accepted this cosmic speed limit as a fact of life. But recently, a new paradigm has emerged, one that promises to unshackle light from its silica prison. It is called hollow core photonics. It involves a counterintuitive feat of engineering, where we trap light not in a solid, but in a vacuum, guiding it through microscopic tunnels of nothingness to achieve speeds 47% faster than standard fiber. This is not science fiction. It is technology currently being deployed beneath the streets of London and Chicago, tested by giants like Microsoft, and raced for by high-frequency traders for whom a nanosecond is worth millions. In this episode, we are going to break down exactly how we learn to trap light in a vacuum, how these cables are made, and why this technology is about to change everything from artificial intelligence to the quantum internet. To understand the magnitude of this breakthrough, we first have to look at the glass prison we currently inhabit. We need to talk about the speed of light. In a vacuum, light travels at what we call c, which is approximately 299, 792, 458 meters per second. This is the universal speed limit. Nothing can go faster. However, when light enters a medium like water or glass, it interacts with the atoms in that material. It gets absorbed and re-emitted, a process that effectively slows it down. This slowing is measured by a number called the refractive index, or N. Standard telecommunications fiber is made of fused silica glass, which has a refractive index of approximately 1.45. If you do the math, taking the speed of light and dividing it by 1.45, you get a velocity of roughly 206,000 kilometers per second. That means that in every fiber optic cable on Earth, from the patch cord at your desk to the massive transatlantic cables, light is traveling at roughly 69% of its potential speed. For a long time, this latency was negligible. Nobody really cares if an email arrives in 100 milliseconds or 150 milliseconds. But as our hunger for real-time data exploded, this 31% tax on speed became a massive bottleneck. We see this in high-frequency trading, where algorithms battle for queue position in microseconds. We see it in massive parallel computing clusters used to train AI models like GPT-4, where the latency between graphical processing units, or GPUs, limits how large a cluster can grow. The solution seems obvious, right? Just remove the glass. If we could guide light through air, which has a refractive index almost identical to a vacuum, we could recover that lost speed. But light, by its nature, wants to spread out. It doesn't want to travel in a straight line forever. So how do you force a beam of light to stay confined in a hollow tube without leaking away? This brings us to the physics of nothing. To make hollow core fiber work, engineers had to abandon the principle that has defined fiber optics since Charles Kao won the Nobel Prize for it. Standard fiber uses total internal reflection. Imagine a core of high refractive index glass surrounded by a cladding of lower refractive index glass. When light tries to escape the core, it hits the boundary at a shallow angle and bounces back in, exactly like a stone skipping on water. But here is the problem. You cannot have a material with a refractive index lower than 1.0, which is the index of a vacuum. Therefore, you cannot use total internal reflection to guide light inside a vacuum core because there is no solid cladding material with a lower index to bounce it off. The laws of physics seem to forbid it. The breakthrough required a totally new way of thinking. In the 1990s, Philip Russell and his team at the University of Southampton proposed the idea of photonic band gaps. Just as a semiconductor crystal has band gaps where electrons cannot exist, a photonic crystal, a material with a periodic structure of microscopic air holes, could prohibit light from existing in the cladding. If the cladding forbids light, and the core is a hollow defect in that crystal, the light has nowhere to go but down the hollow core. This gave birth to the photonic bandgap fiber. Under a microscope, these looked like honeycombs, with hundreds of tiny air holes surrounding a central hollow core. They worked, but they were imperfect. They were lossy, meaning the signal degraded quickly, and they were incredibly difficult to manufacture. The real game changer came later, with a shift from band gaps to something called anti-resonance. I want you to imagine a soap bubble floating in the air. When light hits the thin film of the bubble, some reflects off the outer surface, and some reflects off the inner surface. At specific thicknesses, these reflections interfere with each other. Researchers realized they could surround a hollow core, not with a complex honeycomb, but with a simple ring of thin glass tubes. If the glass walls of these tubes are the exact right thickness, they act as anti-resonant reflecting optical waveguides. When light tries to escape the hollow core and hit the glass wall acts like a highly reflective mirror due to destructive interference in the glass membrane. It pushes the light back into the air core. This design is called nested anti-resonant nodeless fiber, or NANF. This design changed the world for 3 reasons. First, unlike the honeycomb fibers, NANF reflects a massive range of wavelengths, covering the entire spectrum of telecommunications data. Second, it has ultra-low loss. In solid fiber, light travels through the glass. In NANF, light travels through the air and only touches the glass walls occasionally. Third, it has low nonlinearity. In solid glass, if you pump intense laser pulses, the glass distorts the signal. In air, these effects are 1,000 times weaker. You can pump massive amounts of power into a hollow core without the signal garbling itself. Now, let's talk about the engineering marvel of how this is actually made. Manufacturing NANF is a feat of extreme precision. It is often compared to blowing a glass flute longer than the Burj Khalifa. It starts with a preform. Engineers hand-assemble a bundle of glass capillaries or tubes inside a larger glass tube. This bundle is the macroscopic version of the fiber, perhaps 2 to 3 centimeters wide. The arrangement is critical. Typically, 6 smaller tubes are arranged in a ring inside the outer tube, and often smaller tubes are nested inside those. This preform is placed at the top of a fiber draw tower, which is a multi-story vertical factory. A furnace melts the bottom of the preform, and gravity pulls a thin thread of glass downward. Here lies the magic. If you just pulled the glass, the holes would collapse under surface tension. Engineers must pressurize the inside of the hollow tubes with inert gas while pulling. They must independently control the pressure in the central core, the cladding tubes, and the nesting tubes. By balancing the downward pull speed, the furnace temperature, and the internal gas pressures, the 3-centimeter preform is stretched into a hair-thin fiber, just 125 microns wide, while maintaining the perfect internal geometry. The glass membranes in the final fiber are often less than 1 micron thick, thinner than a red blood cell, and must remain uniform over kilometers of length. Recent breakthroughs by companies like Luminicity, which is now part of Microsoft, have achieved lengths of over 10 kilometers with record low loss, proving that this isn't just a lab curiosity, it is scalable manufacturing. So, who is using this? The first killer application was high-frequency trading. In the financial world, the tick-to-trade time, the time it takes to receive a market price update and execute a trade, is the single most important metric. The most famous route in trading is the path between the futures markets in Chicago and the equity markets in New Jersey. The straight-line distance is roughly 730 miles. Light in a vacuum could theoretically do this trip in 3.9 milliseconds one way. Solid fiber takes about 6 milliseconds. For years, traders abandoned fiber for microwave towers to get closer to the speed of light in air. But microwaves have low bandwidth and fade in the rain. Hollow core fiber offers the speed of microwave with the bandwidth and reliability of fiber. In 2022 and 2023, U-Networks deployed the first commercial hollow core cables in London. The gain was a 30% reduction in latency. Light in hollow core fiber saves approximately 1.54 microseconds per kilometer compared to solid fiber. Over a short 7-kilometer metro link, that is about 10 microseconds. 10 microseconds sounds trivial to you and me. But in high-frequency trading, where order queues are first in, first out, arriving 1 microsecond ahead of a competitor determines whether you buy a stock at $100 flat or $100.01. That penny difference, multiplied by millions of shares, is an empire. This race to zero has driven the early adoption, with financial firms paying huge premiums for these dark hollow core strands. But while traders want speed for profit, the tech giants want speed for intelligence. In late 2022, Microsoft shocked the optical industry by acquiring Luminicity. Why? Because of artificial intelligence. Training massive large language models requires thousands of GPUs working in unison. They must constantly exchange parameters, weights, and biases. If one GPU has to wait for data from another, the entire cluster stalls. This is known as the tail latency problem. To keep latency low, data centers today pack GPUs into tight clusters. But you can only pack so much power and heat into one building before you melt the grid. You need to spread the cluster across multiple buildings. Because hollow core fiber moves light 50% faster, it effectively expands the synchronous radius of a data center. If your maximum allowable latency for synchronous training is 10 microseconds, solid fiber allows your GPUs to be about 2 kilometers apart. With hollow core fiber, that same time budget allows you to place GPUs 3 kilometers apart. This increases the area of the circle by a factor of 2.25. Microsoft can now build data center campuses that are spatially larger, easier to cool, easier to power, while the AI models feel like they are all in the same room. For a company planning to deploy millions of GPUs, this geographical flexibility is worth billions in infrastructure savings. Beyond finance and AI, hollow core photonics solves a looming crisis in general telecommunications, energy density. Solid core fibers have a non-linear limit. If you pump too much laser power into glass, the glass interacts with the light, creating noise that destroys the signal. This limits how much data you can send before you need a repeater or amplifier to boost the signal. Hollow core fibers have almost zero non-linearity. You can theoretically pump 100 to 1,000 times more power into an air core than a glass core. If you can launch a signal with 100 times more power, it can travel significantly further before it fades to the noise floor. This means you need fewer electronic repeaters and amplifiers along the ocean floor or across a continent. Repeaters are expensive, they break, and they consume electricity. A hollow core network could be a, quote, passive network over much longer distances, drastically reducing the carbon footprint of the internet. It also plays a role in future 6G networks. Future 6G networks will rely on coordinated multipoint, where multiple cell towers talk to your phone simultaneously to boost speed. This requires the towers to be perfectly synchronized in time. The ultra-stable, low-latency nature of hollow core fiber makes it the ideal synchronization cable for the wireless networks of the 2030s. Of course, there are still challenges. The first is loss, or attenuation. Historically, hollow core fibers lost a lot of signal, but recent double-nested designs have hit 0.174 decibels per kilometer, which is comparable to, and in some spectrum bands even better than, solid fiber. We have effectively solved the loss problem in the lab, but consistent mass production is still ramping up. The second challenge is splicing. You cannot just melt two hollow tubes together. The holes would collapse. Splicing hollow core fiber to standard solid fiber requires complex adapters and careful thermal management. And finally, cost. Currently, it is a boutique product. But like solar panels or SSDs, the price is expected to collapse as manufacturing volume increases. In conclusion, we are witnessing a rare moment in hardware history, a fundamental substitution of the medium of transmission. For 5,000 years, humanity used copper wires. For the last 50 years, we used solid glass. Now we are moving to vacuum. Hollow core photonics is not just an incremental upgrade, it is a step change. It brings the speed of light in vacuum, the fundamental speed limit of the universe, down to the physical layer of our internet. For the trader, it is profit. For the AI engineer, it is a brain that spans miles. For the gamer, it is the end of lag. And for humanity, it is the shattering of the glass ceiling that has capped our communication speeds for half a century. The future is hollow, and it is traveling at 299,792, 458 meters per second. Thanks for listening to G Fun Facts Online, and we will see you in the next deep dive.